Okay, can you hear me? Can you see me? Isaac or Genesis?
Yes, doctor.
Yes, doctor.
Okay, thank you. So we can do something similar to this for the surface forces. Okay, in this case, for example, we have something like this. And now we have forces on the surface acting in the y direction. So again, this is dx. Now the surface of this element is going to be dl, that's the length along this perimeter, times dx, which is this one. Okay, in this case, so we said the force per unit area is going to be traction, is in the local, that's why we point in this direction, and it's the local is in the y direction, that's there. Okay, so this is force per unit area. Okay, and remember the difference between this and the other one is that this one is contact. In our case, the classical is pressure, and that's something that we need to consider. So we said, okay, the differential force is equal to the force per unit area times the area, as we said here. Okay, so it's going to be dl times dx. Usually, we do not have any influence of the position along this perimeter. So we consider that for this position, x position, this element, this function does not vary with L. So if we consider that up here, down here, and in the back, the force within area will be the same. So it doesn't depend on the position, but it can depend on the x position. So we could say that dFs, we are going to express it as L times T times dx. And again, this is going to be, this is the length of the perimeter. So this is going to be force per unit length. Okay. We have to be careful because the P, we use it for several elements, including pressure. So in this case, we have to be careful because this is force per unit length. Okay. See if we can replicate that. Okay, so the potential energy, in this case is surface forces, is going to be the integration in general of dx dl, that's a general, and we say that we multiply that by, I'm sorry, it's traction. This is, so it's going to be traction local in the x, okay, and we multiply by b. That's, so that's this is force, up to here is force, multiplied by displacement, that's potential energy. So again, there's going to be no dependence on this or this, so the integration of that will give us an L, and the result is going to be force per unit length. So this one here, remember, is equal to the D transpose, so I'm going to take it outside there. The integration of that is L. And we consider this constant section, so we took it out. We can take it, we put a key constant section beam. This is something that we said before, so I just want to remind you. So that's that. I'm sorry, we can leave it inside, so we can, yeah, we can express that as, and then we go integrate from 0 to L, and then we say that this is L times T Y, can depend on X, and then this is multiplied by N. So this is a vector, remember, this is 4 by 1, and this is force per unit length, so we can express this as P there. And what we can have to do is we have to express this explicitly as force per unit length, and we multiply that and then integrate. So we say we have to express P multiply it by each element of this vector. And of course, we have to integrate. Remember, these are polynomials, so it's easy to integrate. We have to be careful because there are several terms. That's the only complexity. So let me go back here. These are the ends. If somebody is worried about the evaluation, you don't need to be worried, because if I ask you to do something like this, I'm going to give you these expressions. So you don't need to keep this in your memory. Okay. So the thing is that if I give you that, you should be able to remember how to get into the final evaluations of the equivalent forces in moment. Okay. So that's your responsibility. So if I have something like this, okay, again, so this is, for example, okay, so it's going to be a distribution. So this is P of X. So this is force because of the pressure or because of shear stress or something like that you're applying between these and these points. So you know this function. You multiply by each element of this n vector, and at the results, when we do these integrations, you get this force, this force. In this case, since we have a variation, I don't know which one is going to be larger. And then if you're pushing upward, this has to be probably like this, and this one's going to be probably like that. So that's the idea. Any questions about this, people? Any questions about this? Okay, before we break, let's say a couple of words about, in the case of the pressure. Okay, so let's suppose we have a beam like this. Okay, so this is my local reference system. Okay. Let's change color, green. This is my global reference system. And probably this Y is in the vertical direction, since we have, for example, a free surface here, like this. Okay, so let's go, oh man, let's put it in here. This dimension, let's call it H, for example, H1. And up to this point, from the free surface, we call it H2. Are you with me, people? So probably the pressure here will be like that. Let's call it P1. And here we have the pressure P2. And of course, we have a linear variation there. Okay, so this is pressure. Or no, so this is force per unit length. So P1, this is force per unit length. So it's going to be the pressure. Let's call it pressure, PR, that's pressure at 1 times the spacing. That's a spacing between frames. That it's a data that engineer Isaac provided to you. Okay, so this is, oh shoot, I lost my, here. So this is pressure at joint 1. And this is spacing. Okay, of course, this is equal to gamma times H1 times S. Now, this is force per unit length. So in general here, we need force per unit length as function of the position. So we could have a linear interpolation, and we can say that this is equal to the force per unit length at joint 1 plus the slope. The slope is going to be P2 minus P1 divided by L. So L is the length of the bear times X. And you can express all of this as function of gamma and the height at point 1 and point 2. This is a linear expression. And what you are going to do is you can convert that into the local reference system. So let's use blue. So you're going to convert that into, see, remember, this is your local reference system. So when you proceed and you integrate and you obtain, probably you see that we have more pressure here. So this vector is going to be longer than this one here. Since you are having, I'm sorry. In this case, we have to be careful with the directions. So probably this value will be negative too, because it's pointing in the opposite direction as a positive. If you point downward, this moment is going to be like that, and this moment is going to be like that, and you see that this is smaller than this one in general value. And from this, if you want to solve, you have to take this, you have to take components in the global reference system. Let me draw that. There. People, questions?
Doctor, I have a question.
Yeah. Who's this?
Ordóñez.
Okay, go on, Ordóñez.
About the pressure that you found in the pressure PR1 when find a specific weight times. Yes.
Yeah, okay. Time H1.
Yes. H1, in that case, that pressure is horizontal. On one super.
No. Remember that pressure acts perpendicular to the surface.
Yes.
Yeah, that's why I draw it like this, perpendicular to the surface.
So we don't need to do another geometric formulation,
Transformation,
but
no.
transformation. That is always
Yeah,
perpendicular.
that's okay. So
Um,
remember that if you want, you can do it, but it's in this case, see, this is a 2D problem. It's you can try to you are masking this. So see, I obtain. Let me go back one step. This transformation, clearly, we're talking about the local reference system, clearly, right? So what I'm showing you is that these blue vectors are clearly in the local reference system, okay, in the local. So what you can do is you can obtain those from the local to the global, yes. So this is using the T matrix. This is the what? This is the, this is, no, this is the, no, that's it, yeah.
Yeah.
Exactly. So since in this case you have this, what you can do is you can go the other way. You can go this is equal to D transpose times local D. So you have this instead of, I'm sorry. See, I'm not transforming displacement, I'm transforming forces. See, I'm transforming forces. So it's going to be, let's call it F, because it's for the one element, F, F, and F. So this is the way we replaced to obtain the global matrix. I'm sorry, the stiffness matrix of an element in a global reference system. So what you have to do is take this one here. Remember, the inverse of this T is equal to the transpose. And you know this. But this operation, you can do it. But you'll see that it's basically this. You have to be careful with the theta angle, and that's all. Ordóñez, did I answer your concern?
Yes, my concern was about more to the pressure or direction to the pressure when I calculate with the formula, but I know I got it.
Okay, I'm glad. Any other question, people? Any other question? No? Okay, so you have all the material that you need to complete the assignment. So in some cases, you have inclining elements, and you have to do something like this in order to consider the distribution of force per unit length on each element, and you can proceed and go on with the calculations. Okay, people, next Thursday, we're going to present the derivation of the stiffness matrix for the beam element. And that's something that we know. I would like to answer questions about this project. And then next Monday, we're going to do another progress control. Even though we don't have classes, we can do that in the same at the same time. Okay. And then on Wednesday, we can have the presentation. We are going to have the presentations, and that's it. Any questions, people? Any questions? Some of the groups are well, some of the groups are a little bit behind, so try to catch up. Okay.
Question.
Yeah, go on.
About the inertia.
Okay. The sectional inertia, go on.
The calculate is for element or all.
Yeah, no, we need, see, in general, for example, let's suppose I'm going to draw something strange, okay? This is just to show you to answer your concern. So we have a plate like this. Let's suppose we have a plate on the side, and this is a plate on the bottom, right? Let's suppose that this plate has a thickness T side, and this is a thickness which is different in the bottom. Let's suppose. And here we have a flat bar. Believe it or not, that's on a straight line. And here we have another flat bar there. So this is plate. So we have thickness here and so on. So if we make a cut here, we have an spacing and a flat bar. This is for the side. And we have the same spacing. Okay, the spacing is the same, but this thickness here is different. So the spacing is the same, but the properties of this part here are different in general than the properties in the side. So you need to calculate the sectional inertia of this and apply it in elements in this part, and another sectional inertia for the bottom. So yeah, you need to calculate different sectional inertia in general. It's possible that you have uniform properties. In that case, yes, it's going to be a single value. But in general, you need to calculate the properties of each section. It's part of the structure. Kumbe?
Okay, thank you.
No problem. Any other question? Final question, people. Isaac, I need your help. I'm having a very different time schedule. So please, would you take my office hours tonight? I have office hours from 8 to 9. Would you attend those office hours, Isaac?
Okay.
So, people, Engineer Isaac will be available to answer questions from 8 to 9 instead of me, because I have a completely different time schedule where I'm right now, and I have very difficult times trying to catching up. Okay, I have a class from 7 to 9, so I don't have the time to be with you. But Isaac can answer questions about the project. Okay, people, see you. Isaac and